Thank you. My name is Ben Langmuir, and I'd like to talk to you today about caching explicit Clang modules using content-addressable storage. Last year, my colleague Stephen and I talked about adding content-addressable storage library to LLVM and using it as part of a caching system. In particular, we talked about a system for caching whole Clang compilations. This is similar to a tool like Ccache, but done inside the compiler, allowing us to do it with improved soundness and performance. This year, I'd like to talk about how we extended that system to support Clang modules. First, a quick introduction to content-addressable storage and its role in our caching system. In content-addressable storage, or a CAS, data is stored where the object's address is given by a hash of the contents. That means we get a one-to-one mapping between a CAS identifier and a given piece of data. Any change in the data means we get a different CAS identifier. So how does that relate to caching? Well, the idea is we're going to pull all of our compilation inputs into the CAS, as well as all of our outputs. On the input side, we have a structured representation of a compilation, including a command line invocation, as well as some representation of all of the input files involved. On the output side, we also have a structured representation, including, say, an object file, as well as any diagnostics. We form an association between the CAS identifier at the top of each of these trees. We do that using an append-only key-value data store that we call our action cache. Next, I'd like to talk about how we use this in Clang compilation caching. The basic idea is that we're going to map all of our inputs into the CAS in order to isolate ourselves from the mutable file system. This is to make caching sound. Specifically, we'll run the Clang dependency scanner to find all of the inputs, pulling them into CAS objects as we go. We'll build a new command line invocation that only has access to CAS inputs. We can capture outputs, and finally, we can cache the results knowing that we have a fully sound pure computation. Let's talk about that input discovery. We can run the Clang dependency scanner on this simple translation unit. We'll use our new experimental include tree full output format. The output from the dependency scanner is a structured representation covering all of the modules and translation units involved. Lots of information gets stored in this output, but we're going to focus on the command line invocation. This is the command that would build that particular module or translation unit. When caching is enabled, we have a new command line argument, fcas include tree, which has a CAS identifier. We can use a tool to print out the contents of our include tree so that we can see this representation of input files. At the top level, we have a representation of our main file. This is a main.c name, followed by a CAS identifier. This CAS identifier points to the contents of that original main file. If we get a cache miss and need to recompile this buffer is where we're going to start our parsing from. Next, we have our first include of a header. For this, we represent a source location where that header was included, the file name, and again, the contents of the header in the CAS object. In this case, we have a further include, and so you can see this tree structure develop where each include gets a nested location underneath of its includer. The next thing in our include tree is the include for c.h. You can see we completely skipped over the declaration code that was in between. This is because the Clang dependency scanner is designed to very efficiently skip over code not involved in dependency analysis. Lastly, and what's new this year, we have a representation for a modular import. Again, we have a source location, and then we need some way to import this module. Let's talk about what goes on here. First, I'll talk about how we're going to compile this module in a way that is compatible with caching. The main file for a Clang module can be thought of as the module map file. Now, this would be a bit different for a C++ module or header unit. Again, our dependency scanner output has a representation for this module, including the command line we're going to use to build it. And again, it has an include tree. Some parts of our module map have a straightforward implementation in the include tree. Our header declarations become includes in our include tree. In this case, the top level of our include tree is the virtual module includes buffer that the compiler generates. Next, we need to keep track at each header include location what submodule we're entering or exiting. This allows us to associate declarations and macro definitions from this module with the correct submodule. Finally, any additional metadata that was in our module map, such as the link and export declarations here, gets stored in a simplified module map data structure at the end of our include tree. This design means that when we go to compile the module, that is, in the case of a cache miss, our compilation does not need to reparse module map files, look up modules or headers, or use virtual file systems or header maps. All of this information gets computed once during our dependency scan, and we can then drive the compilation directly from the include tree. Taking the invocation and include tree, we have the representation of our cache key. We can use our action cache to associate that with our outputs, and we now have enough information to cache our compilation of the module. Now let's talk about how we're going to import that module into our translation unit. Going back to the include tree for our translation unit, one natural idea would be to include a cast reference that points to the contents of the compiled module or PCM file. Unfortunately, this approach doesn't quite work. At scan time, we haven't yet compiled the module, so we have no way to refer to it by a cast ID that depends on its contents. If we wanted to support this design, we would have to run the scan intermixed with the build in dependency order, which would be bad for performance. Our solution for this is to instead use a new command line argument, fmodule file cache key, that associates a given module PCM path with a cast identifier. But in this case, we're not referring to the contents of the module, but instead the cache key that was used to build it. That is the invocation and the include tree. Because we know we would get the same cache key when we actually compile the module, we can look up its contents in our action cache. This design means that compilation can be pure for both the module and the translation unit. We can compute all of our cache keys during the dependency scan in parallel like it is today. And then we can look up the contents of modules or look for cache hits in our action cache. With these two pieces, we have everything we need in order to cache both the compilation of the module and the compilation of the translation unit that imports it. Today, I talked briefly about how we extended compilation caching to support Clang modules. This is one application of content-addressable storage, or CAS. If you're interested in additional applications, my colleague Shubham is giving a talk tomorrow talking about storing debug information in the CAS. If you'd like to see this work upstream as much as I would, we'd love you to take a look at our in-progress CAS review patches. Thank you.